Pushing deeper into the microscopic world, past individual cells, toward the scale of atoms, traditional glass lenses eventually hit a dead stop. Standard optical microscopes operate under a strict physical constraint. They rely on visible light, which operates at a wavelength between roughly 400 and 700 nanometers. This comparison table shows exactly how that limits us. Because of the size of that visible light wave, it is physically impossible to resolve any two objects that sit closer together than about 200 nanometers. The wave simply washes over them. That limit locks us out of the nanoscale. Seeing individual atoms, the protein spikes on a virus, or a cell's internal machinery is physically impossible with traditional optics. To bypass this optical ceiling, we have to completely abandon the photon and find a much smaller source of illumination. That replacement source is the electron. Specifically, a steady stream of electrons accelerated under high voltage. This works because of the de Broglie hypothesis in quantum mechanics, which proves that moving particles actually exhibit their own wave-like properties. When an electron is fired at 100,000 volts, its wavelength compresses violently. Returning to our table, this accelerated electron's wavelength drops to 0.0037 nanometers. That is 100,000 times shorter than visible light, pushing maximum resolution to the sub-nanometer scale. But because electrons are charged particles, you cannot push them through glass lenses. They have to be shaped and focused by powerful circular electromagnets. Escaping the limits of visible light means trading your simple, familiar desktop microscope for a massive, highly sensitive metal tower. The physical architecture of an electron microscope begins with this towering metal column, housing an electron gun at the absolute top. Every system built on this platform shares one non-negotiable operational rule. The entire column must run under an ultra-high vacuum. If you leave even a trace amount of air inside the chamber, the electrons will collide with oxygen and nitrogen molecules. The beam will scatter instantly before it ever hits the sample. This creates an immediate biological trade-off. Under an ultra-high vacuum, the water inside a living cell instantly boils. You cannot keep an organism alive through the observation process. There is also an optical trade-off. Electrons do not carry color data. The final output you receive is a strictly grayscale map. To view reality at the atomic level, you have to trade the colorful, living, ambient world for a dead grayscale vacuum. Within that vacuum, researchers generally choose between two distinct operational architectures. The first is the Transmission Electron Microscope, or TEM, built to look straight through matter. The TEM fires a broad, continuous beam of electrons directly down the column toward the specimen. To ensure those electrons can physically pass through, sample preparation is brutal. Technicians embed the target in resin and slice it with a diamond knife until it is less than 100 nanometers thick. This two-dimensional cross-section shows the mechanics at work. The dense atomic areas of the sample scatter the beam, creating dark spots. The thinner areas let the electrons pass cleanly down to the detector below, registering as bright light. Look at the grayscale micrograph pinned to this flip chart. That is the authentic sub-nanometer two-dimensional cross-section that the TEM generates. While the TEM provides unparalleled maps of internal atomic structures, the intense physical slicing required leaves the sample highly vulnerable to preparation artifacts. The competing architecture takes the opposite approach. The Scanning Electron Microscope, or SEM, is designed to look at a surface rather than pass through it. Instead of a broad beam, the SEM uses its electromagnets to choke the electrons into a microscopic pinpoint. Deflector coils sweep that pinpoint row by row across the surface. As this topographical diagram shows, the primary beam strikes the sample and knocks loose secondary electrons from the surface itself. A detector positioned off to the side catches these secondary sparks. Because the beam strikes the outside of the object, biological or non-conductive samples must first be sputter-coated in an ultra-thin layer of gold or platinum to conduct the static charge away. Check the monitors on the right side of this desk. These digital workstations render the detector data into incredibly deep, three-dimensional-looking grayscale topographies. The SEM sacrifices the sub-nanometer internal resolution of the TEM and requires a metal coating, but it remains the primary tool for mapping the complex 3D reality of a surface. You have likely seen heavily detailed, brightly colored images of insect faces attributed to these machines. Remember the core rule of the shared platform. Electrons do not carry visible color data. Those vibrant images are constructed after the fact. Technicians take the raw grayscale data into software like Photoshop and meticulously paint in false colors to highlight structures and engage viewers. Ultimately, these machines function as high-precision sensors that translate density and topography into a data-driven map. This decision tree shows how labs choose between these multi-million-dollar models. The evaluation starts with a single question: what is your target? If your objective is quality control on a semiconductor, inspecting nanoscale fractures, or analyzing topography, you map straight to the SEM. If you need to verify the exact atomic lattice of a new aerospace alloy, or map the internal protein structure of a specific virus, you accept the grueling sample prep and invest in the TEM. And if your mandate is to observe living cell division or study a subject in its natural ambient reality, you keep your budget intact and stick with an optical light microscope. The entire discipline is built on a strict trade-off scale, balancing sample preparation difficulty against total resolution yield. In the end, the hardware you choose relies entirely on which specific dimension of reality you need to measure.